This is example number 2 on cumulative damage. For this particular example, let's consider this step function where it has a radius here, a small radius here. You have a diameter and you have a d. The radius is given by 0.1. Please note that in this particular example, r is not equal to d minus d over 2. This might be good in a small shaft, but usually in bigger shafts where you have a big step, you never want this to be very high, right? You want to stay there. You want this R to be in the bulk range of 125. In some cases where it is a big concern, it may go up to 125, but that's rare, so you want to stay around this. That's a clarification. This particular part is machined from titanium alloy, and it has the following loading condition. It's a completely reversed loading condition, and is given by the following plot. It's completely reversed, and you can see it has a zero mean here. Um, that's the pattern that it has, and has a constant bending stress of this value. And during a typical 30-second operation under operating conditions, the nominal stress, so it gives me the diameter as 1 inch, was measured as shown in the figure. That's the one you have in the next figure. You want a 95% of survivability, and you want an additional factor of 1.2. So let's see in this problem, this is what I have. This is a 30-second test that was taken. And what you can see here, when you're trying to evaluate and understand how these tests work, you look at the peaks here. So one peak is at 10. So one of the peaks is at 10. You have another peak that shows up at 20. You have another peak that shows up at 25. You have another peak that shows up here at 35. Okay, those are your actually tau 1. Let's call this tau 2. Let's call this tau 3. We have to call this tau 4, and this is all nominal. Okay, then how many amplitudes does this repeat itself? You count at 10. You go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So, and 4 repeats 13 times. So that's it cycles 13. And then you want to find what these ends are for each one of these cases. At 20, you have 20, 1, 2, 3, and 4. So this is equal to 4. At 25, you have 1 and 2. It's equal to 2. And at 35, you only have 1. Okay, so this is how the loading sequence works in a 30-second test. The problem does give me the ultimate and tensile strengths for this particular example problem. Also, you have your fully modified endurance limit that's given already calculated for you. Your values of B and A are given as follows. So this is the equation of N that we will be using for the rest of the exercise. Okay, so as we move on now, before we do anything, this is a step function and you're working fatigue. So we need to find, that's a nominal stresses, that's what you have. So we need to find your stress concentrations by using your corresponding tables. I don't have any axial load, so that's why I don't have anything for axial. So this is 1.75 for static. This is static. And for torsion. And then going to the tables, corresponding tables for titanium, you can show that this is approximate equal to 0.83 and 0.86. There's a different charts for this, not the ones that you have in your textbook. So it approximately gives you that. So that would give you a value of fatigue stress in bending 1.62 and 1.40 for shear. Okay, now that we have this, we should go ahead and apply our uh, we should go and apply uh, our design factor. So this we know in the problem. So we need to go ahead and apply the design factor. So the new bending stress will be the bending stress that's given in the problem multiplied by my design factor. That will be 3.08 multiplied by 1.2 gives me 3.70, and multiplying all of my taus, tau 1 would be 35 times 1.2, that would give me 42. Tau 2 would be 30, 25 times 1.2, that gives me 30. Tau 3 will be 20 times 1.2, that gives me 24. And tau 4 is equal to 10 times 1.2, and that gives me 12. So these are the stresses that I'm going to use all the way across. Okay, so as we move on now, what we want to do in the problem is, let me set up for you what your state of stresses will look like in the general case. So for the alternate, your state of stress is going to look as follows. You're going to have all zeros. You multiply your kf here, alternate, 0, 0, 0, 0, 0, 0. And you're wondering why I have all, kfs tau. And you're wondering why we have all this alternate. Well, if you actually evaluate this, you will find that FB minus FB, that would give you, divided by 2 gives you 0, so there's no alternate. The only thing that you have really left is your mean, that will be a constant value, and that's just because your load is completely constant. That's why you can do that, okay? And then for your mean case, this will be KFB XX mean, and you do have your alternate uh, mean and alternate, although this is all 0 as well. And you can see in the problem, all my alternate stresses will be 0 because the mean is is a fully reversed. So you know that in this problem, these components will be 0, this will be 0, and this is 0 because it's static, right? It's a static load, so therefore we don't need to do anything. So you can do this problem. And the other thing you want to keep in mind is, since this is completely, so this is how we do this problem. So now let's just move on. So now we're going to go ahead and let me divide this in 4 parts. Okay, so we're going to do this for each one of the loading conditions. So I'm going to have loading condition number 1 that says tau is equal to 1, and sigma 1 is equal to 3.70. So tau 2 will be 30. Tau 3 will be 24. Tau 4 will be 12. And sigma 2 will be 3.7. Sigma 3 will be 3.7. And sigma 4 will be 3.7, right? These are the loading conditions. And don't forget, this is constant. This is constant, 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 and this is all fully reversed. So from here, you can build a state of stress. You can build a state of stress for this case, a state of stress for all of these cases, state of stress, state of stress, state of stress, state of stress. And then from this state of stress, you're going to find your von Mises, and that's going to be your SA. So you find your von Mises stress. Okay, we're going to call this S1. And the value for this von Mises stress will be 101.5. You find your mean. This will be equivalent von Mises from this case. And this will give you 6. And then you do the same thing for each one of these cases. This is your von Mises, okay? That comes from this. This gives you 72.5. This is your von Mises, and this gives you 6. Von Mises, you get a value of 58. Your von Mises in mean gives you 6. Your von Mises in alternating von Mises gives you 29, and your mean, you get a value of 6. Then the first check that we do is the static check. So static check is we add this plus this, and you want to make sure that all these are less or equal than sigma yield. Okay, so sigma yield has a value. Sigma yield in tensile had a value of 128. That was given in the problem. That was given right here. So this value is known, is given. So let's compare all these values. So in this case, I get a sigma max of 107.7. You can see that this is less than this, so we are good. Here's sigma max. You add these two and you get 78.5. If we are less than this, so we are good. Sigma max 3 will be, you add these up and you get 64. This is less than this value, so we are good. Sigma max in 4 is equal to 35, and it's also less than 124 or 128. So we are also good. So now we can proceed, and I wish I could continue down here, but I can't. But we're going to go ahead and continue this in the next table. And for each one of those cases that I found, so we found these guys. So each one of these cases, now we're going to find the Goodman stress. That's going to be SA1 divided by 1 minus SM1 divided by ultimate tensile. If you evaluate this, you get equal to 1. The value that you get here is 106. Here, the value that you get for this value using the same equation, but for S2, this is S2, this is 2. You get a value of 78. Here you get a value of 60. Here you get a value of 30. Okay, so first thing, you have to make sure that these are all less than, this is less than sigma yield. In tensile, this is 128. So this is less than 128, less than 128, less than 128. So we are good in yield. So the last check we do is to see if we have finite life or infinite life. So in this particular problem, I move to the next page. So I have to compare with SE. Remember that SE in the problem was given as 32. So I know the value of SE. SE is 32. And you can see that S equivalent 1 is less than, is bigger than this. So I have finite life. Here, this is 2. This is bigger than SE. You can see this is bigger than SE, so I have finite life. Here, this is also bigger than SE, okay? And this is also this is actually less than SE. So here, immediately, I know that my life is equal to infinite life. Here, I need to use my equation to find my life. So I use this equation over A 1 over B. Okay, so you use this equation and you find that you get a value of 0.82 times 10 to the 3. And then here you get a value of 7 and 2 gives you 7.37 times 10 to the 3. Here, and 3 is equal to 2.2631 times 10 to the 4. Okay, so now we move to the next item. So we want to know how much life of my structure I have. So I'm going to basically use this equation here where we have all the values now. And we found that this particular case, and 4, there has to be less or equal than 1. We know that this was infinite. So 1 over infinite gives you 0. So this goes away. And these are the only ones that are remaining. Okay, and this was equal to 1, this was equal to 2, this was equal to 4, this was equal to 13, but this is 0. And where does that come from? This comes from your evaluation of your how many amplitudes do you have for that loading cycle. Okay, so once we have done that, so then the next step is basically I did all the problem for you here. You want to take the inverse of this and find your BF. And to find your BF, that will give you a number of duty cycles. The problem states that doing a typical 30-second operation. Okay, this is a typical 30-second operation. In one duty cycle, I have, this gives you duty cycles, by the way. This is in terms of duty cycles. One duty cycle has 30 seconds, 60 seconds in a minute, 60 minutes in 1 hour, have about 6.5 hours left of life. This is very low, so you really should redesign your part. The part needs redesign. Okay, and you can compare, you can decide how much life you want in the structure. Many times, if you want a 1-year warranty, then you put here 1-year warranty, find how many. You can keep on multiplying this in terms of days and years, and then you can come up with a number here in terms of years. For a 1-year warranty, you have to make sure that this can be at least 1 year. You don't want it to be too long, but you don't want it to be less than 1 year. So this is kind of, this should be less or equal than 1, less or equal than this. So your BF for this example is 6.18 hours. Less than that, that's why it's approximately 6 hours. So this is how you will do these problems. And this is end of example number 2 on fatigue.